With improper integrals, one way or the other, infinity is involved. The first type of improper integral that we're going to take a look at is one where the interval of integration is infinite. Either your lower limit is negative infinity, your upper limit is positive infinity, or it's possible that you're looking at an integral from negative infinity to positive infinity. And stupid computer, there we go. Okay, so here's an example of an improper integral that has an infinite limit. This one is the lower limit. The problem with this is that the way we use the fundamental theorem to evaluate a definite integral, we anti-differentiate and then plug in the upper limit and the lower limit. Well, the issue arises when we look at that lower limit. If it's negative infinity, it's really not legal for us to substitute negative infinity in an expression. So the way that we get around that is by rewriting that integral as a definite integral from b to negative 4 of our function. And we work this integral and then calculate the limit as b approaches negative infinity. So, pause the recording and do what you can to integrate from b to negative 4 the function 1 over x plus 3 quantity cubed. If you have tried that on your own now, let's go through the steps. Okay, I'm going to let u be the quantity x plus 3. So du is 1. And with u substitution in the past, we've changed the limits. I don't want to do that this time. I think that makes it harder. So what we're going to we're going to do the substitution and rewrite the integrand, but we're not going to mess with the limits. We're just going to make sure that we replace u in our antiderivative with the quantity x plus 3 before we plug in the b and the negative 4. So we're bending the rules just a little bit because it makes our lives a little easier. The antiderivative would be negative 1 over 2 u cubed that would be u squared, not u cubed. And notice that I write the limit as b approaches negative infinity on every line. That can't just disappear and then show back up again at the bottom when you're ready to use it. Replacing u with x plus 3. Now we're ready to substitute negative 4 and b in that antiderivative. So negative 1 over 2 times negative 1 squared minus negative 1 over 2 times b plus 3 squared. Cleaning that up just a little bit then. We're looking at negative 1/2 plus 1 over 2 times the quantity b plus 3 squared. Now as b approaches infinity, this fraction that has a power of b in the denominator, that's going to go to 0. So taking the limit as b approaches negative infinity results in our getting a value negative 1/2. So we can say that the definite integral from negative infinity to negative 4 of the function 1 over the quantity x plus 3 cubed dx is equal to negative 1/2. So this limit converges. If you don't get a value for the limit when you work it, in other words, if you end up with infinity or negative infinity, then the limit diverges. Limits will infinite limits are either going to converge if you get a value, or they'll diverge if you don't get a finite value. So that brings up our next example. If I have a definite integral from 1 to positive infinity of the quantity 1 over x to the p power, we want to take a look at what powers are going to allow this integral to converge. So start by rewriting the problem as the limit as b approaches infinity I just realized that I made a mistake in that first problem. So let's back up and take a look at what I did wrong. And it's really, what we did, the work we did was fine, just the notation was a little bit off. When it's the lower limit that's infinite, we typically replace that with an a, because we think about intervals from a to b. So we would start at a, and so every place that I've got a b, I really should have an a. So I'm going to fix that. So the limit as a approaches negative infinity of the integral from a to negative 4. And the notation is going to be much better now. That limit still converges. We're still going to get a value of negative 1/2. Okay, so this limit, since the upper limit is the one that's infinite, limit as b approaches infinity is what I want to do for a definite integral from 1 to b of 1 over x to the p power dx. And it would probably be helpful to write that as x to the minus p power dx. Anti-differentiating. The new power on x would be negative p plus 1, and then we're going to divide by 1 over that new power using the power rule for integrals. And then the limits are 1 to b. Okay, now we're looking at a limit as b approaches infinity. The quantity 1 over 1 minus p, I would rewrite that as 1 minus p instead of negative p plus 1. That quantity, for all intents and purposes in this example, in this particular limit, that I've got highlighted in yellow there is constant. So I'm going to go ahead and pull that out in front. So 1 over 1 minus p is multiplied by the limit as b approaches infinity of x to the 1 minus p power. And then that is evaluated from 1 to b. So we're looking at b to the 1 minus p power minus 1 to the 1 minus p power. Now thinking about what has to happen here if we're going to be able to, well, I can simplify one more step before I start thinking about that. Cleaning this up just a little bit more. 1 raised to any power is just going to be 1. So that looks better. A little bit simpler and going to be easier for me to think about my limit. Now, for us to get a value for this limit, to be able to say that the integral converges, we really need b to the 1 minus p power to go to 0. As b approaches infinity, we need that particular power of b to go to 0. We know that's going to be the case if b, the power of b, is in the denominator. So I need the power, 1 minus p, to be a negative number so that the power of b is in the denominator of a fraction, and then when we take the limit as b approaches infinity, that fraction's value goes to 0. So thinking that 1 minus p has to be less than 0, negative p has to be less than negative 1, which means positive p needs to be greater than 1. So this integral will converge for any values of p greater than 1. So the integral from 1 to infinity of 1 over x to the p power dx converges for p, values of p greater than 1. That's a better way of saying that.